So it's my distinct pleasure to introduce Praneeth Netrapalli. Welcome to the session of the RDA, and we're looking forward to exciting talks throughout the session. And it's my distinct pleasure to introduce Praneeth Netrapalli. And I'll just keep it short because there's a lot to talk about. Praneeth is currently a research scientist at Google Research India and an adjunct professor at TIFR, as well as a faculty associate of ICPS, right? And so he's had a long and distinguished career while being at Microsoft Research India, as well as UT Austin and Goldman Sachs. He has done quite a lot of very interesting work in designing robust machine learning algorithms, right, as well as other black box optimization techniques, as well as he's also been awarded for a lot of this. And over to you, Praneeth. I'm looking forward to hear from you. I'm very excited.
Thank you, Anirban. And firstly, thanks to the organizers for organizing this workshop and also inviting me. I want to talk about a couple of different aspects of like there are several algorithmic aspects in stochastic optimization that we have worked on in the recent past. And over the two talks, I want to discuss two of them. And the ideas, at least like the fundamental technical ideas, have a lot in common. So I hope that the first talk can serve as kind of a primer in understanding how these things are analyzed. And in the second talk, I'll use this to kind of describe also like another new algorithmic idea that we came up with recently and which seems quite interesting to us. Okay, so yeah, was there a question? Okay, so this is joint work with many wonderful collaborators, and the one that I'm going to be talking today about is joint work with Prateek Jain, Shyam Kakade, Rahul Kidambi, and Aaron Sexton.
I request everybody to please be on mute. Thank you.
Okay. So let me begin with an overview. So as all of us are perhaps aware of, optimization is a big part of large-scale machine learning, and stochastic gradient descent is the workhorse in most of the practical applications. And while stochastic gradient descent is very widely used and has been observed to have very good empirical performance, there are several aspects of SGD that are important for its good practical performance. And some of the examples include what is the size of mini batch that we use in running SGD, and how can we distribute SGD to work over multiple machines, and how do we do acceleration, which is a optimization technique to speed up convergence, and what is the kind of learning rate schedule that we use as time progresses. And similarly, what do we do when we are encountered not with independent data but dependent data, such as the ones that arise in say time series analysis or reinforcement learning and so on. Okay. So as I mentioned, like while SGD is widely used and has been observed to have very good performance, these aspects and how exactly each of these is tuned is actually quite important for its good practical performance. So our work has been to do a thorough investigation of all of these aspects, particularly for linear regression and also beyond linear regression, at least in some settings theoretically and in several settings also empirically. Okay. So in this talk, I'll particularly be talking about two aspects. So in the first talk, which is today, I'll be talking about acceleration and how we can extend what does acceleration mean in stochastic gradient descent, and how do we extend acceleration from deterministic optimization to stochastic optimization. And in the second talk tomorrow, I'll be talking more about how do we learn with dependent data. And the reason I'm talking about like two different things is that the underlying analysis tools and techniques are quite related, and they share a lot of the underlying ideas. So today I'll be talking about like the first thing, which is acceleration, and tomorrow I'll be talking about learning with dependent data. Okay. And again, so if there is any question at any point of time, please feel free to stop me. I'll be happy to answer questions right away. So let me begin with like a brief introduction of optimization. So one of the most fundamental and classical algorithms for optimization is gradient descent and goes all the way back to Cauchy. And the idea is that if you would like to minimize a function f over a parameter space w, then gradient descent looks at what is the direction in which the function decreases the most if I were to move like unit direction. And the next iterate wt plus 1 is nothing but w2. minus a delta step size, which is called the step size delta, times the gradient direction. Okay, so this is gradient descent, and it's classical and of course like very well known. And we'll also be particularly looking at the problem of linear regression, where the function f is given by the following equation, where we have a matrix X, each row of X transpose is called a sample, and we have a column vector Y, and each element of Y is called an observation. So our problem would be that we want to find a W which minimizes the L2 norm square of X transpose W minus Y. And this is, of course, a very fundamental problem and arises pervasively in applications. So this is deeply studied in literature because in addition to its importance as a standalone problem, it's also used as a subroutine in many other problem settings as well. And that's the reason why this problem has been studied so deeply. So one of the first questions that we'll ask ourselves in this context is, what if we apply gradient descent to solve linear regression, then what is the guarantee that we can get? Right? And in this case, firstly, the update takes the following simple form, where the gradient can be computed in this form. So we have X times X transpose W2 minus B. So X transpose, so this should actually be the same as Y. Sorry for the typo. Yeah, so X transpose WT minus Y, B or Y. So this thing is basically the residual, and we are combining the columns of X according to their residuals, and then we move in the negative gradient direction. Which is what gradient descent does. So in order to state the performance guarantee of gradient descent for linear regression, we need to introduce a little bit of notation. So let f star be the minimizing value of the function f. Okay, and then we define the condition number of this problem as the ratio of the smallest to largest singular value of the matrix XX transpose. Okay, you look at the matrix XX transpose, and we look at the ratio of the largest to smallest singular value, and this is called the condition number. And if our goal is to find a W such that f of W minus f star is less than or equal to epsilon, right? Convergence rate basically means the number of iterations of gradient descent that is required in order to find a W which satisfies this condition. Okay, and it is well known that gradient descent requires a number of iterations which scales linearly in the condition number. So it's kappa times a logarithmic factor that depends on the initial suboptimality f of W0 minus f star divided by the final target suboptimality epsilon. Okay, so the important point here is that the convergence rate scales linearly in the condition number. Any question? Okay. So a natural question is whether it's possible to do better than gradient descent in terms of this convergence rate. And the hope is that gradient descent actually does not reuse past gradients, right? It only looks at the gradient at WT, and when it goes to WT plus 1, it no longer looks at all the past gradients. And the hope is that somehow maybe we can reuse past gradients to actually do better. And the answer actually turns out to be yes. And there have been several celebrated algorithms, including conjugate gradient, heavy ball method, accelerated gradient, and so on, which actually improve the convergence rate of gradient descent for different classes of problems. Okay? And these algorithms all share, like at a fundamental level, they all have some similarity, and consequently, all of these methods together are known as momentum methods. So let me explain how one of these methods, in particular, like the Nesterov's accelerated gradient method, looks like compared to the gradient descent algorithm. Okay, so in Nesterov's accelerated gradient, we have two iterates, WT and VT, whereas in gradient descent we only had one iterate, right? And also there are two kinds of steps. From VT, we take gradient steps, and this gives us WT plus 1. And from WT plus 1, we take a momentum step, which is basically, we look at how WT has changed to WT plus 1. So we want to shoot further in this direction, and this is called a momentum step, and this gives us VT plus 1. Okay, so in the notation that we just established in the previous slide, where f star stands for the minimum value of f, and kappa stands for the condition number of XX transpose, right? The convergence rate of Nesterov's accelerated gradient descent turns out to be a square root of condition number times the logarithmic factor, whereas for gradient descent, it was linear in condition number, right? Yeah. So so in terms of equations, the algorithms again looks very similar to gradient descent, where the per step computation, right? So where WT plus 1 is being updated as VT minus the delta times the gradient of VT, and VT Vt plus 1 is Wt plus 1 plus like the momentum factor from Wt plus 1 to Wt, right? So so in terms of per step computation, all we are doing is we are just computing one gradient. And
परसों पेपर है मेरा.
is there a question? Okay. So yeah, so in terms of per step computation, all I was trying to say was that the order of the per step computation is the same for both Nesterov's accelerated gradient as well as gradient descent. However, the number of iterations taken is much smaller for Nesterov's accelerated gradient, where it is square root kappa compared to kappa for the gradient descent algorithm. So note that this is a ratio of max over min, so this is always greater than or equal to 1. So square root kappa is indeed less than or equal to kappa, right? And right, this is what I was trying to say. And it's not just a theoretical improvement, even on like moderate condition number problems. In this case, for example, where the condition number is of the order of 100, we can see that accelerated gradient descent is actually an order of magnitude faster compared to gradient descent. So accelerated gradient descent is widely used in practice in several applications in solving not only linear regression problems, but also other convex optimization problems.
One question.
So, yeah.
So, are there some assumptions on F in these momentum-based methods?
Yeah. So this guarantee can be proved for any function f which is smooth and convex. What is meant by smooth is that roughly you can think that the Hessian you can replace this condition number to be condition number of the Hessian at a point, and then you want to say that the maximum condition number of the Hessian at any point in the space is bounded by kappa. Then you get this kind of guarantee. Does it make sense?
But no extra guarantees compared to gradient descent convergence rates.
What do you mean by no extra guarantee? So gradient descent can only get a kappa, whereas here we are getting a square root kappa.
Yeah, but there also you need these assumptions like convexity.
Right. So, I mean, beyond convexity, it's hard to really say a lot of things. So there is work which tries to identify rates of convergence to local minima or even like stationary points, where you define optimality not as like closeness to minimizer, but maybe norm of the gradient or whether the Hessian is almost positive, semi-definite, and so on. So even in those cases, we have been able to show that Nesterov's accelerated gradient can get improved convergence compared to gradient descent, but the convergence is not a global minima.
Yeah, thanks.
Hey, Praneeth, so you've written theta in the convergence rate. Is that to suggest that this, like, there are functions for which you do need these many iterations?
That's correct. Yeah. Yeah.
Okay.
Actually, yeah. And even this one is actually theta in the sense that you can design problems for which it cannot be better than, for any given value of kappa, you can design a problem for which it cannot be better. Yeah.
And how do you pick those delta gamma terms, or any sufficiently small step size?
So you have to choose them carefully. You have to choose them carefully, which depends on like the problem parameters, like the condition number, and gamma also depends on. Yeah. So there are two parameters that will be used to determine delta and gamma. One is the condition number. The other one is the value of the sigma max. So these are the two parameters that will be required.
And you don't change them with time. It's fixed.
Gamma, yeah. So if you only care about, so there are two kinds of algorithms. One is anytime algorithm. There you don't want to fix t a priori. So you want to say that I just want to keep running the algorithm, and if I query it at any point t, I should get a point which satisfies some guarantee depending on t, right?
Right.
So there you would vary like gamma with respect to t. Delta will not change, but gamma will change. But in the other case, you fix a priori that I'm going to run it for like 1,000 or 10,000 or whatever, like some number of steps. Then you don't have to vary it with t. You can use a constant.
Okay. Got it.
Okay. Sounds good. So this was all like a primer more on standard optimization. So let me come in particular to optimization the way it's usually done in machine learning, which also leads us to the stochastic optimization problem. So the basic setting is that we observe n samples, so x1, y1 all the way up to xn, yn. All of these are drawn from some distribution of RD cross R. And we again want to minimize this function f hat, which is given by 1 over n summation over I xi transpose w minus yi whole square. Okay. While we are given these n samples, our actual goal is not necessarily to minimize f hat, but rather to minimize the function which is of the same form, the linear regression problem, but where xy are actually drawn from the distribution, and then we take an expectation over this quantity, right? So the difference between these two is that this is called the population version, where you're actually writing out the expectation. And this is called the empirical version, where you draw samples from the distribution and try to hope that this approximates this function, right? And if you want to directly solve this, gradient descent is not directly applicable, because you like the gradient would again be written as expectations, and we cannot compute exact expectations, right? So people have studied this in the context of stochastic approximation. Again, has a very long history, going back 60 or 70 years. And let me now explain what this. So what people have, like what is the algorithm that people have developed in this context, where we are getting samples and not expectations from the underlying distribution. So the original algorithm goes back to Robbins and Monro, and that's a paper which actually first introduced stochastic gradient descent. And the main idea is that instead of computing the gradient of f, you replace it with grad hat f, where grad hat f is actually computed just using a single sample xt comma yt. Okay. The nice property of grad hat f is that the expectation, when you take expectation over xt comma yt, is equal to the gradient of f at wt. And eventually, what do we return? So it turns out that instead of returning the final quantity, because this is a stochastic algorithm, it turns out that it's better to actually return some kind of average. And we can return something called a tail average, where we average over the last so many iterations and then return that as the final solution, right? And for linear regression, SGD is particularly popular because it takes the very simple form, where given a sample xt comma yt, you just compute xt transpose wt minus yt times xt. So this requires only one matrix vector product, and then this again like a linear vector operation, right? And one of the reasons for its popularity is that it's actually a streaming algorithm, where you look at one sample, you take an update, and then you move on to the next sample, and so on. And this is the reason why it's widely used in practice. Right. So just like we could change gradient descent to stochastic gradient descent, we can ask whether we can convert these momentum algorithms also to their stochastic counterparts, where we don't have access to exact gradients, but we only have this access to stochastic gradients, right? So you can easily like replace the gradients with stochastic gradients, and then with heavy ball you get a stochastic heavy ball method. With Nesterov's accelerated gradient, you again get stochastic Nesterov's accelerated gradient method, right? And the question is, like, what can we say first about the convergence rate of stochastic gradient descent, and also about the stochastic momentum methods, right? So let's first look at the convergence rate of stochastic gradient descent, and in particular, let's also consider the special case where there is no noise, meaning that there exists a true W star, so that Y is exactly equal to X transpose W star. Okay. Using similar arguments as in the gradient descent convergence rate, we can argue that the convergence rate is again linear in the condition, is actually slightly different expression, which basically goes like the denominator is exactly the same, which is the smallest singular value of a singular value. It turns we can replace it with the maximum norm of x square. Okay. So this is the notion of condition number. It turns out that this is the right notion of condition number for the stochastic setting. And the convergence rate again is this linear in condition number times a logarithmic factor that depends on the initial and targets of optimalities. And finally, in the noisy case, where Y is actually equal to X transpose W star plus some zero mean additive noise, there is an additive term in this convergence rate which depends on the variance of the noise, which is sigma square, which is defined as expected value of n square. Okay. Any question about the convergence rate of SGD? Okay. Okay, so let's summarize like what we had known
quick
until
question,
like our work. Yeah, yeah.
So this notion of condition number that you said, any short intuition you could give us? Why is that the right notion? Because the numerator looked a little strange. Why is that the right notion of condition number?
So you can think of it this way. So every time, okay, so in earlier the gradient descent, So WT was being multiplied by XX transpose. I'm not sure if you remember. Right. So the gradient has WT was being multiplied by XX transpose, right? And what comes here is actually the maximum singular value of whatever is being multiplied here. Okay. So in order to ensure that it's kind of stable, so like you'll require step size to be smaller than. So if this quantity is large, then delta has to be small, and that's why it enters into the convergence rate, right? So here it's the maximum singular value of this XX transpose that was appearing here. So in this case, if you look at the term that's sitting WT, it's actually XT transpose, right? So if you look at the norm of this rank 1 XT transpose matrix, that's nothing but the norm of X square, norm of X square. So that's yeah. So that's the reason you'll be you'll be forced to choose a step which is small compared to XT square. Okay. Okay. So.
Hey, quick
Right.
question, Praneeth. Yeah, before
Yeah.
you go. So this max is over this samples, like so it's max over
support,
T.
yeah, over the support of the distribution. Yeah.
And is it that fragile, as in can't like?
Yeah. So you can replace it with a fourth moment kind of quantity.
Okay.
So, but I did not want to.
Fine. Yes.
Make the notation
Right.
more cumbersome.
No. Thanks.
Yeah, but you can replace it with some fourth moment related quantity. Okay, sounds good. Sounds good. So, is there a delay? Hello.
Your voice is a little choppy sometimes.
So let me maybe continue. If there is any issue. Okay. Okay, let me know. I'll try to do something. Okay. So just to summarize, like the current situation, like all the results that we have seen so far. So in the deterministic case, we have seen that gradient descent has a convergence rate which depends linearly on the condition number, and momentum methods such as Nesterov's accelerated gradient descent were able to improve the condition number dependence to a square root of condition number, right? And in the stochastic setting, where we were only processing one sample per step, we saw that stochastic gradient descent again has a linear dependence on condition number. And the question we were asking was whether we can accelerate stochastic gradient descent even in the stochastic setting. Is the question clear? Hello.
Yeah, it's clear. Right. Yeah.
Okay. Thanks. Sorry, I was just pinging just to make sure that I have not lost connection and I'm just going on and on and so on. Yeah. Okay. Sounds good. So this is the main question that we would like to understand. And it turns out that the second quantity that we have here, it's actually indeed optimal statistically. So information theoretically, we cannot do better than this. So the question is, can we actually improve the first term that's appearing in this one? Okay. And first, let me convince you that this is actually important, because in most of the implementations of SGD, even like when we are trying to use them to solve like train neural networks and so on, the algorithms that are currently available actually use a stochastic variant of Nesterov's accelerated gradient descent. And while in the deterministic setting, we have seen that it can actually give orders of magnitude improvement both in theory and in practice. It turns out that theoretically there has been no prior work which tries to understand whether momentum can actually improve convergence rate even in the stochastic setting. Okay, and there have been some papers which try to investigate the effect of momentum in the stochastic setting, but it's not in the machine learning setting where we are getting samples one at a time and so on. And I'll be happy to discuss offline about like the difference in the stochastic models that are used in the prior work compared to the ones that we are more interested in studying. Okay. So the bottom line is that the first term can actually be improved to something better. And let me first give you an outline of our result. So the first result is actually an impossibility result, which says that you cannot always improve the condition number dependence to a square root of condition number. So this is actually a negative result. But at the same time, we would like to understand whether improvement is ever possible. And then we are able to show that there are some settings where improvement is indeed possible. So the third question is whether existing algorithms such as the stochastic variants of these heavy ball and Nesterov's accelerated gradient, whether they can actually achieve this improvement. And it turns out that they cannot, and in fact, they are no better than stochastic gradient descent. And finally, we are able to design a new algorithm called accelerated stochastic gradient descent, which can probably improve the condition number dependence to something better whenever information theoretically it is possible. Okay. So let me run you through each of these briefly before I go into a bit more detail on the final part. Okay. So the first question was whether acceleration is always possible, and let us give like a counter example to argue that it is indeed possible. So let's consider the noiseless setting where y is exactly equal to x transpose w star, and we have already seen that the SGD convergence rate is linear in the condition number. Okay, and we are hoping that whether an accelerated rate of say square root condition number is indeed possible, right? So there is no second term because this is noiseless, and second term just disappears. So the example that we would like to look at is a discrete distribution where x is just 1, 0 with like very high probability and 0, 1 with very low probability. Okay, and in this case, we can indeed compute the condition number, which turns out to be 10 to the 4 because the norm of x square is equal to 1 with probability 1, right? And when it comes to the Hessian, it is diagonal with elements 0.999 and 0.001. So the smallest value of the Hessian is just 0.0001. And so the condition is 10 to the 4. And the question we are asking whether a convergence rate of square root condition number times logarithmic factor is possible. And it turns out that so this is equivalent to at least either version of this is asking whether we count the error using a square root condition number or 100 samples, right? And what we first observe is that if you have fewer than 100 samples, it means that we do not observe this element at all, which means that we cannot compute. So because this is a second basis vector, we cannot estimate the second component of W star at all. Okay, what this shows us is that we can actually do no better than a linear dependence on condition number. So in particular, acceleration is not possible for this distribution, and so it's not possible in general. Okay, so we cannot always improve the linear dependence on condition number to a square root condition number. So any questions about this or this example?
So just a quick comment. So then, is it true that here you are assuming that the definition of SGD, which is a definition, is that the samples are chosen uniformly at random. If there's some non-uniform distribution, then this example does not hold. Am I correct in thinking about that?
That's correct. So what we want to say is that whether you can improve the dependence from condition number to square root condition number. So you cannot always hope for an improvement. So you cannot design an algorithm which always does this improvement, because there are some cases where this improvement is not possible information theoretically. So
I wanted to say is that if SGD is somehow choosing samples non-uniformly, then this doesn't rule that out, right?
Right. So here SGD is actually okay. So the setting that we are in is that you only have access to uniform samples from the given distribution. So you are in the streaming setting where this is the only access you have, and this is like an information theoretical argument that no algorithm can work in this setting. Right. So let's now look at a different example, which is the Gaussian distribution, where the Hessian is again the same as in the previous example, 0.9999 and 0.0001. However, in this case, so even though the condition number is again like 10 to the 4, because we see that the vectors are always of unit norm with high probability or like constant norm, and the smallest singular value of the Hessian is still 0.0001. So the condition number is again 10 to the 4. However, even when we get two samples, just because of the properties of Gaussian distribution, we know that the empirical covariance matrix xi transpose is actually invertible, right? So we can actually invert this matrix to find W star. So it is indeed possible to find W star just after 2 samples, which is much smaller than the condition number 10 to the 4, right? So at least information theoretically, acceleration might be possible for this distribution. So again, like even here, we are getting only uniform samples from the distribution, but the distribution here is Gaussian. So the answer to the second question is that acceleration might be possible under some settings, but it does depend on other problem parameters, right? So when we dig deeper on what is the information theoretic quantity that can help us achieve faster convergence of the underlying parameter, we see that the key difference between the previous and this setting is that the empirical covariance matrix here concentrates much better so we have much better spectral concentration of the empirical covariance matrix to the true covariance matrix as compared to in the previous example. And one of the key quantities that tells us how fast this spectral concentration happens is called matrix variance. Okay, so let me be a bit more concrete. So let's say we have this xi coming from a distribution D, and let's say H is the expected covariance matrix of xi, right? And what we want to argue is that we want to say that we want to find a number of samples n such that the empirical covariance matrix is close to the true covariance matrix H. Okay, and the question is how many samples n are required in order to guarantee this. If xi was just a scalar, we know that variance gives us a good quantity, or in general, like maybe higher moments if you want high probability guarantees, right? So so variance, which is the variance of this x square quantity, is basically what tells us how many samples we need to collect in order for the empirical average to be close to the true average. And in the context of matrices, there is a similar quantity called matrix variance, and we call this the statistical condition number, which I'll describe next. So the statistical condition number can be defined as follows. So let's say H is the covariance matrix, the expected covariance matrix of xi transpose, right? So we look at say a given direction E, right? And so on that particular direction, the condition number is more like what is the average value of xi in this direction. So we look at the norm of E transpose xi whole square divided by the expected value that this quantity takes, okay, for any given vector E, and then we sum it across all the different eigen direction basis of the matrix H. Okay. So this basically tells us that we can have larger norm in some directions, but it's just that the corresponding, as long as the corresponding expected value is also large, then we'll be able to approximate that direction fairly quickly. So this is what is called the statistical condition number. On the other hand, what we are calling the computational condition number is actually taking a summation over the numerator, but replacing the denominator by minimum over all directions E. This is what gives us the minimum eigenvector of the Hessian matrix. So in this sense, so once we pose it like this, it's clear that the statistical condition number is actually smaller than the computational condition number always. And our previous matrix concentration example suggests us that acceleration might be possible if the statistical condition number is much smaller than the condition number kappa. Okay. So any questions on this one? Okay. Okay, so let's compute the statistical condition number versus the computational condition number for the discrete as well as the Gaussian distributions that we saw earlier. So for the discrete distribution, it turns out that the statistical condition number is still of the order of 10 to the 4, which is the same as the computational condition number. Whereas for the Gaussian distribution, it turns out that the statistical condition number is only about 100 compared to 10 to the 4 in the computational of the 10 to the 4, which is the computational condition number. So in this case, the statistical condition number is much smaller than the computational condition number, and we would expect acceleration to be at least information theoretically feasible in this setting, whereas it may not be feasible at all in this setting. Okay. And so just to give an illustration of how these SGD behaves on these two different settings. So the left plot is the behavior of SGD for the discrete distribution, and the right one is for the Gaussian distribution. The green curve plots the error versus the number of iterations. Okay, and the pink dotted line indicates the statistical condition number on the x-axis in both the plots. Okay, so here it's of the order of 10 to the 4, whereas here it's of the order of 100, and we can see that the geometric decay, or like the sharp decay, starts pretty much about the computational condition number for the discrete setting. And even for the Gaussian setting, even though statistical condition number is much smaller, the drop again seems to happen pretty much at the same point, right? What this suggests is that even though information theoretically it may be possible to achieve a faster convergence rate, SGD itself is not achieving that faster convergence rate, and the sharp decay is still happening on the at around like the 10 to the 4 samples, which is the value of the computational condition number. Okay, so given that SGD is not achieving acceleration even when it is possible, the next question we wanted to ask was whether existing algorithms such as like stochastic momentum methods, can they achieve this improvement? And it turns out that the answer is again no, and we are able to construct distributions where the statistical condition number is actually much smaller than the computational condition number, but the rate of stochastic heavy ball method is no better than a linear dependence on the condition number. Okay, and the same statement actually seems true even for empirically, it seems true even for Nesterov's accelerated gradient descent. However, we have not been able to prove this statement for the accelerated gradient algorithm. And I should also mention that the distributions that we construct here are fairly natural, not very bad cooked up, not like very badly cooked up distributions, but rather seem fairly natural. And the point is that the stochastic versions of existing algorithms do not really seem to provide an improvement over stochastic gradient descent, even for these reasonably benign distributions. Okay. Right. So as we can see from this plot, the behavior of empirical behavior of both stochastic heavy ball and Nesterov's accelerated gradient is not much better than that of stochastic gradient descent. So let's now come to the final question that we were asking, which is whether we can design an algorithm which can improve over stochastic gradient descent and achieve acceleration whenever it is possible. And the answer is yes. And it turns out that we can, so we are able to design an algorithm that we call accelerated stochastic gradient descent, which improves the dependence of on condition number kappa to be a square root of kappa times kappa twiddle. Okay? Because we have already shown that kappa twiddle is always less than or equal to kappa, this number is always an improvement over the condition number. And in cases where kappa twiddle is much smaller than kappa, this can be much smaller compared to kappa. So is the sound clear? Any question about the result?
So quick question. So like this, the statistical condition number is smaller, but is there still a complementary bound saying that it'll be, let's say, the dimension times kappa, or can the ratio be really large, like unbounded? So probably
the ratio can actually be, yeah. So the ratio can actually be unbounded. So for example, if you take the Gaussian distribution, kappa twiddle will always be equal to the and kappa can be arbitrarily large.
By skewing the Hessian, like just picking a
by skewing the Hessian. That's correct. Okay. That's correct. So kappa twiddle for Gaussians is always equal to dimension. Yeah.
Okay.
Okay. Yeah. Thanks.
And you don't need the, so it's not like the a priori knowledge of these condition numbers that matters. It's just that like the standard stochastic gradient isn't able to leverage this.
That's correct. Right. Right. So, I mean, even in our algorithm, at least to set the parameters and everything, we need the knowledge of kappa twiddle and kappa. But even if you give that kind of knowledge, it's just that SGD is not able to do the right updates. So it's more about the form of the updates rather than the knowledge of these parameters.
So, okay, yeah, maybe like final question. So, like, why is SGD not doing well for the Gaussian? So, I'm just wondering that plot, is there some intuition to understand like the waterfall diagram that you showed in one of the previous slides, that even
Right.
for the Gaussian case where this kappa tilde is fixed constant, SGD actually has a really long warm-up period before it starts dropping.
Right.
So why?
So
why
again, yeah. So the main reason, I mean, the main reason again comes from the deterministic setting. So even the deterministic setting, for example, there is no statistical aspect there, right? And even there, gradient descent is not able to improve because it cannot choose a very large step size because you will diverge in the larger eigen direction. And if you choose a smaller step size, then your progress in the smaller direction will always be limited. And that's the same reason even in this setting. And accelerated gradient descent, somehow it's able to use updates which kind of simultaneously do faster progress in the lower eigen directions without really blowing up in the larger eigen directions. And somehow like the key idea is how to do this in the stochastic setting. So for those of you maybe who are familiar with like Chebyshev polynomials, the improvement from kappa to square root kappa, at least in the deterministic setting, is again like related to the fact that so Chebyshev, right? So if you want to go from 0 to 1 in a very small interval delta while being bounded in the domain 0 to 1, then the degree of the polynomial required is of the order 1 over square root delta. So it basically follows from the same thing. Basically that you want to design a polynomial which does not blow up in the larger eigen directions. And at the same time, it also has faster, like it's close to 0 in all the in the entire eigen space, right? So
so it's this balancing act that kind of forces the
right. So SGD is doing the like naive polynomial, whereas Nesterov's accelerated gradient is taking advantage of the fact that you can design better polynomials, like lower degree polynomials which can still do this. Yeah.
Correct. Thanks.
Yeah. Right. So yeah, before I go into the like ideas of the proof and so on, so let me just show the empirical evaluation of these algorithms. So again, like the green thing is the stochastic gradient descent. The black and blue, which are pretty much overlapping, are the stochastic versions of Hibby-Ball and Nesterov's accelerated gradient, which are currently implemented. And this red one is the algorithm that we developed. And we can see that there is at least an order of magnitude improvement in terms of the convergence rate compared to both stochastic gradient descent and the stochastic versions of these prior algorithms. And we also note that there is still a significant amount of gap between like the lower bound, which is kappa twiddle. This is the information theoretic lower bound, and the convergence rate of our algorithm. And so while we do not have a lower bound better than kappa twiddle, we believe that doing anything better than the square root of kappa twiddle might not be possible once you account for computational restrictions. So yeah, but again, like we do not have a proof for this statement. So let me describe the algorithm in a bit more detail. Yeah.
Yeah. So let me just ask one question. So for the specific case of the Gaussian, you can do better, right? You can just estimate the Hessian and then.
Right. So I guess what I'm saying is for a streaming stochastic algorithm, so in particular, you can maintain memory only linear in D. Maintaining the Hessian will require you to have memory D square.
Right.
So if you're allowed memory only D, like all the algorithms that we know of are of this flavor, and we do not know how to improve over something like this. Yeah.
Got it.
Yeah. Thanks, Siddharth, for the questions. So let me, in the remaining like 10 to 15 minutes. So let me briefly describe the algorithm and the main ideas behind the proof. So it turns out that there are several equivalent versions of Nesterov's accelerated gradient in the deterministic setting, and we write the algorithm in different ways depending on different intuitions, like whether we look at it as a primal dual algorithm or whether we have a slightly modified potential function that it's doing, or whether we look at it as a discretization of Newton's equations of motion, right? So there are different ways of looking at Nesterov's accelerated gradient descent, and depending on which way you look at it, you can parameterize the algorithm in different ways. And in particular, like there is one formulation which has both an upper and lower bound interpretation, which is much less popular in terms of like the way it's implemented, because as you can imagine, like a 2-iterate version is much more compact to write, whereas the 4-iterate version is much more elaborate. But it turns out that this 4-iterate version actually captures the essence of what we want to do even in the stochastic setting. So the idea is the following. So right. So we have 4 different iterates: U, V, W, and Z. And what we are doing is we are doing gradient descents at some points. So for example, Vt minus 1 is a gradient descent at Wt minus 1, but using gradient at a different point. Okay. So we do gradient descents starting from one point, but using gradients of a different point. Okay. Sorry. Sorry, I misspoke. Okay, so we have 2 different endpoints, U0 and U and Z, and we take a point Vt minus 1, which is on the line between U and Z, and then we do a gradient descent at Vt minus 1 that gives us the next iterate Wt, and similarly we do a gradient descent at a different point Zt minus 1, but we use gradients of Vt minus 1 again to get a new point Ut. Okay, so the algorithm is slightly complicated, and maybe it's difficult to explain the intuition behind this in the short talk. But let me go to the proof and try to expand how to explain how to where some of these aspects come from. So we recall our guarantee that we can replace the linear dependence on condition number with the square root of condition number times the statistical condition number. And as we saw, the first term actually depends on initial error, and the second one is the statistical error, right? And we can actually do 2 different analysis for the 2 terms. And for the first term, we can just analyze the problem assuming that there is no noise and sigma equal to 0. For the second term, we analyze assuming that W0 is equal to W star, so that this term disappears and only the second term remains. Okay. So for the first part, we actually use a potential function, which is pretty much inspired by the deterministic analysis of the deterministic version of accelerated gradient descent that I described here. So the main idea is that use a potential function where you track the distance between Wt and W star in the Hessian norm, and at the same time you track the distance between Vt and W star in the L2 square norm. Okay. From a intuitive point of view, what this is trying to do is this is the function value difference. So this is like the primal bound, and this is the dual bound because we'll always be using gradients at Vt, and gradients at Vt certify a lower bound on the function value. Okay, so the potential function is a combination of a primal value and then also a dual value. So this is indeed a primal dual method, and the key change that we do in the stochastic setting is that when we look at the H here, it turns out that the so the bounds that we get are much worse. So in order to deal with that, what we do is that we observe that we can actually, so as long as we fix the eigenbasis of H, right? So we can think of H as a diagonal matrix. It's just that we are using different weights for different coordinates here, whereas we are using the same weight for all the coordinates here. We can actually shift the weights in the same way in both of these terms. So when we multiply this with H inverse on both the sides, we get a L2 square norm here and a H inverse square norm here. Okay, and once we do this, it turns out that the guarantee, so we can convert the same analysis in the deterministic setting, where the convergence rate can now be bounded by 1 minus 1 over square root of kappa kappa twiddle, and this is what gives us the square root of kappa kappa twiddle convergence rate in the first term. Okay, now the more challenging part was the second part, where we want to analyze the effect of noise. Okay, so in this case, we assume that we are actually, let's say, at W star, and what is the effect of noise. So in order to do this, we look at the following update. So where Wt plus 1, so let's first look at the so we look at Wt plus 1 minus W star and Vt plus 1 minus V star W star, right? We can actually, because everything is linear here, we can actually write this as a linear process where we have a matrix C multiplying WT minus W star, BT minus W star plus some noise. And when we write TT, when we do not using theta T, the covariance matrix of at time T, right? We can again write this like multiply this with its transpose, and then we get again a linear equation for theta T plus 1, which is an operator B times theta T plus noise transpose. Okay, so when we expand this all the way till 0, we see that the final covariance matrix theta n can be written as a power series summation over I b to the I times noise transpose. And because the noise is identical across different time steps, we can replace this with I minus B inverse, where B is this operator. Okay. So the bottom line is that we need to understand this I minus B inverse times noise transpose. And the key challenge in understanding this is that B turns out to be an asymmetric matrix and consequently has singular values which are greater than 1. But however, it turns out that it has eigenvalues smaller than 1. So I minus B inverse indeed is well defined, but we are not able to do naive bounds just using the singular decomposition of B, right? And the way we do it is to solve the one-dimensional version of this I minus B inverse times noise transpose using explicit computations. So when B is one-dimensional, and so we do this in every eigendirection corresponding to the Hessian. And once we have this one-dimensional version of this bound, we can combine all these one-dimensional bounds using the statistical condition number bounds. And finally, what we get is that the expected value of W minus W star, like the at any iterate t as t goes to infinity, is upper bounded by kappa twiddle H inverse plus delta times identity. So delta is the step size and kappa twiddle is the statistical condition number, and H is the Hessian of the problem. Okay. Okay. So once we note that this is actually the final bound on the final variance of the final iterate, and in order to get a bound on the average iterate, this becomes a bit more complicated because instead of theta T plus 1, we want to understand the covariance matrix of the average iterate. But basically the same kind of arguments can again be applied to bound the average iterate's covariance matrix, and that basically gives us a statistically optimal bound, which is sigma square d over n, while the bias decay rate, which was square root kappa twiddle. So this was gotten using the analysis of the part 1 in the potential function. So any questions about the high level argument? Okay. So to summarize so far, so we have seen that for linear regression, we have completely theoretically understood like the behavior of various algorithms, including SGD, stochastic versions of AB ball, Nesterov accelerated gradient, and then we also designed a new algorithm which improves over all of these algorithms. And the question is, in practice, beyond linear regression, what is one of the first questions that we wanted to understand is, why do stochastic heavy ball and Nesterov accelerated gradient algorithms still work better than stochastic gradient descent in practice? And our nature was that we are mini batching. And what mini batching does is that when we have a large enough sample in the mini batch, then the stochastic gradient is pretty much close to being the actual gradient. So this takes it closer to the deterministic setting, where we know that heavy ball and Nesterov accelerated gradient are indeed giving can give provable advantage over stochastic gradient descent, right? And the precise quantification of small or large depends on the data set and on the problem parameters. And the key advantage of accelerated stochastic gradient descent is that it improves over stochastic gradient descent even for small mini batches. And yeah, so we have some empirical results which show the improvement. Maybe I'll skip this in the interest of time. Yeah, so let me just try to recap. So we saw that in the deterministic case, gradient descent has a linear dependence on condition number. Nesterov's accelerated gradient descent can improve this to a square root of condition number. In the stochastic setting, again, SGT has linear dependence on condition number. and we saw that naively replacing gradients with stochastic gradient descent no longer do not get any improvement over stochastic gradient descent in the stochastic setting. Whereas we were able to design a new accelerated stochastic gradient descent algorithm, which improves the kappa dependence to a square root of kappa twiddle, where kappa twiddle is the statistical condition number. And whenever this is much smaller than kappa, this provides significant improvements. And in practice, this seems to work even beyond linear regression problems. So yeah, so that's all I wanted to say. Happy to answer any further questions.
Questions?
Praneeth, so the lower bound that's known in the stochastic setting is square root k tilde, or is it k tilde?
So again, like that's a good question. It would be kappa twiddle. It's not square root, and that's again. Let me put it this way: that's the tightest known bound known for matrix spectral concentration. What we can show a lower bound for is that if you don't have matrix spectral concentration, you will not be able to solve the problem, right? And this is the best known upper bound for matrix spectral concentration. There are also some lower bounds in some settings, but it's not a per problem kind of lower bound.
Okay. Yeah. So, I mean, I guess what I was trying to understand was like in settings where kappa and kappa tilde are equal or like very close to each other, this is like this accelerated.
This will not be useful. Yeah, this will not do anything better than stochastic gradient descent.
Okay.
Again, like I guess we don't have a lower bound proof like that, showing that it's going to be theta, but like I believe that it will not do better.
Sure. Yeah. Okay, makes sense.
Any other questions? I have one, and ninth one possibly. That is it possible to sort of quickly see to get a sense of whether kappa tilde is much smaller than kappa for a given data set?
Yeah, actually, like for kappa twiddle, we give an explicit expression, so we can indeed compute it, and yeah, so it requires us to compute the Hessian, but it also involves like inverting the Hessian. But if you are able to do that, you can compute kappa twiddle for a given distribution.
I see. Any other questions? We still have a couple of minutes. Okay. If not, let's thank the speaker. I mean, everybody is still on mute, so I'll thank Praneeth for an excellent talk on behalf of everybody. Thank you.
Thank you, Anirban.